Welcome back, everybody. So this is section 3.9, related rates. Related rates. Okay. Now, again, like I said, section 3.9 is all application. Okay, section 3.9 is all application of derivatives. Remind me, what is a derivative? A derivative is the slope, right? Or instantaneous rate of change, right? The derivative is instantaneous rate of change. So if I'm looking for instantaneous change of any sort of quantity, I'm going to need to find the derivative to do so, right? If I'm looking for instantaneous rate of change of speed, I've got to find the derivative. If I'm looking for instantaneous rate of, rate of change of anything, then I have to find the derivative, right? That's like kind of like the end game of all of the first chapter, right? So all we're doing here is looking at applications of instantaneous rate of change. Applications of instantaneous rate of change. Then as you got it, we have we'll do 1, 2, 3, 4 examples today, and then we'll have one on Tuesday. So they're all going to seem very different, but they're going to work in the same manner. If we're pumping air into a balloon, like think about pumping air into a balloon, both the volume and the radius of that balloon are increasing at their rates. And those rates of increase are related to one another, right? As I increase the volume of the balloon, the radius is increasing by a steady amount as well, right? Those rates are related to one another. But it's much easier to measure directly the rate of increase of the volume rather than the rate of increase of the radius of the balloon, right? I could very easily, I guess not very easily, it's easier to calculate the volume directly of that balloon. And you can't really get inside that balloon and calculate how fast the radius is increasing, right? So it's easy to calculate the rate of change of the volume, but not necessarily calculate the rate of change of the radius. In a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity. So if two rates are changing at the same, I don't want to say at the same amount, but in the same manner, if they are related to one another, they're not necessarily changing at the exact same amount, but those rates are related to one another. We can calculate the rate of change of one quantity as it compares to the rate of change of another quantity because they are linked together. Again, in related rates problems, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. Like we can calculate the rate of change of the volume of the balloon and somehow work around the problem of finding the rate of change of the radius of the balloon. The procedure is to find an equation that relates those two quantities together, then use the chain rule to differentiate both sides with respect to time. Okay. Let's do it. And I need to get my notes. I need to have my notes with me because this is a difficult section. I remember last year I didn't have my notes with me this section, and I started calculating it, and it was like I did it a different way than I had in my notes, and things got real messy real quick, and it did not go good. So, air is being pumped into a spherical balloon. And again, we are assuming spherical balloon here. I know balloons are oblong shaped, but we're assuming a spherical balloon. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So taking a look here, I know the rate of change of the volume. The rate of change of the volume is 100 centimeters cubed per second. I want to know how fast the radius of the balloon is increasing. And when do I want to know that? I want to know instantaneous rate of change when the balloon has a diameter of 50 centimeters, right? I want to know how fast the balloon is increasing, how fast the balloon's radius is increasing when the balloon hits 50 centimeters as its diameter. Okay? All right, so let's figure out what we know and what we don't know, right? We know the rate of change of the volume. Now, in terms of the rate of change of the volume, think about the labels on that, right? It's change in volume over time, right? How fast is the balloon's volume changing? That is, we would put it in Leibniz notation as, and I'm going to use Leibniz notation here today because it's just easier to do that rather than prime notation. dv dt, because we can see it means something. dv dt stands for the rate of change of the volume with respect to time. So dv dt is 100. Okay, 100 centimeters cubed per second. That's dv dt. What are we looking for? What are we trying to find? What's the other rate that's related to this? The rate of change of the radius, right? We need to find dr dt. That's what we don't know. Well, when do we want to find this? We want to find this when the diameter is 50. Okay, so in terms of a radius, what is that? 25, right? So when radius is 25. We want to find dr dt when r is 25. We want to find the slope when r is 25. We want to find the instantaneous rate of change when r is 25. So what type of equation fits together volume and radius? Well, the volume formula, right? Think about the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. Volume of a sphere is 4/3 pi r cubed. So again, the goal is to try to find some sort of equation that links the two quantities together. We know the rates are related to one another, so find an equation that links those two quantities together, and maybe you can calculate some sort of derivative. Like for example here. Now, both of these derivatives are with respect to time, right? So this is sort of like implicit differentiation. Is there any sort of time in this equation? No. So I would be able to take the derivative on time and just use my straight up derivative rules if time was part of this equation, but time is not part of that equation. We've only got volume and radius. So it's kind of like implicit differentiation when we say, well, I've got to use the chain rule when something is acting on that variable. Is anything acting on volume? Is any sort of function acting on volume? No, it's just volume, right? It's not like volume cubed or anything, like radius. It's not, nothing's acting on volume. It's not like sine volume. No. So we can just take the derivative of volume by saying, okay, that's dv dt, right? The derivative of volume is dv dt. And then we say, okay, 4/3 pi, and I keep those because that's a loopy looking 3. I keep those because they are coefficients on the r. 4/3 pi. Now, is something acting on r? Yes. So I have to say, well, I've got to take this to the third power, use that, 3 times r squared, right? I just brought it all the way out front, in front of the coefficients even. I know that will reduce. Multiplied by, well, the derivative of r. The derivative of r is dr dt. That's the chain rule, right? Something was acting on r, so I have to find the derivative by taking dr dt. Got to take the derivative of the outer piece, then I've multiplied by dr dt. Okay, well, let's reduce this down a little bit. So dv dt is equal to, those 3's cancel, 4 pi r squared dr dt. Okay, so now I've got an equation with dv dt, r, and dr dt. 2 of those are known. What is dv dt? 100. What is r? 25. I can calculate dr dt. So dv dt is 100, and then I take 4 times pi r 25 squared dr dt, and I can solve this equation for dr dt. All right. So I divide by 4 pi times 25 squared, so this is 100 divided by 4 pi times 25 squared, and that's equal to dr dt. Okay, so really 100 divided by 4 is 25. So that'd be like 25 over pi times 25 squared. So that's really just 1 over pi times 25, I think. 100 divided by, oops, that's parentheses, divided by 4 pi times 25 squared. 0.0127. 0.0127, yep. Which is equivalent 0.0127. Now, think about the label here. That is how fast the radius is changing. Let's go back up to our original problem and say, okay, so we've got centimeters, and radius is a linear length, right? Centimeters per time, centimeters per second. That's how fast the radius is changing. Just by knowing that the volume is changing at a certain rate, I know when I want to take that radius, because the radius might be, how fast the radius changes depends upon when you're taking that measurement, right? I know I wanted to find it at when my radius turned to 50. And when my radius turns to 50, it's increasing at a rate of 0.0127 centimeters per second. All right, let's try a different example. Okay, a ladder 10 foot long rests against a vertical wall. If the bottom of the ladder starts to slide away from the wall, and we can somehow measure the sliding rate of our ladder, the ladder slides away from the wall at a rate of 1 foot per second. How fast does the top of the ladder slide down the wall? And I want to know that when the ladder is 6 feet from the wall. Now, in my opinion, we didn't necessarily need to do this on the last one. It was kind of a pretty straightforward example. It might be best to draw a picture each time. The pictures usually assist you in creating your equations that link one another together. All right, so we've got a vertical wall. Here's my ground. And I have this ladder here. Ladder's 10 foot long. That's not 10 prime. That's not 10 prime. That looks like 10 prime. The ladder's 10 feet long. I know, think about this. If I calculated this in terms of x and y, this x and this y, the bottom of the ladder is going to start to slide away, right? Which is going to cause the top of the ladder to slide down. I know the bottom of the ladder is sliding at a rate. Okay. Oh, I never took attendance. Uh-oh. Hi, Mrs. Brown. Good. How are you doing? I've got no Kaylee or Madison Dempshire either. Sure. Yep. Hi. What is my job? What is the job? I'm working many things. I'm a math teacher. I'm an attendance taker. I'm a grader. All right. Okay, so if I say that this is x and this is y, I know that the rate of change that my ladder is sliding out at, right, it's going this way, I could write that as dx dt, right? The rate of change that my ladder's sliding out is dx dt, and I know that that's 1 foot per second. Do I know how fast my y is changing? No, that's my end goal, right? How fast is the top of the ladder sliding down the wall? So dy dt is what I want to know, right? dy dt is what I want to know. Well, is there some sort of equation that we can relate these two quantities together with? Well, that's a right triangle. I know that I can say x squared plus y squared equals 10 squared. Let's differentiate that. Okay, is there something acting on x? Yeah. So that would be 2x dx dt plus 2y dy dt is equal to, now I would say 100, but I found the derivative. So what goes on the other side? Taking the derivative. 0. Because it would be 100 squared, and I find the derivative of just 100, or sorry, just 10 squared. A 10 squared would be 100, and finding the derivative of 100 would just be 0. Okay, now here's the deal. I have this unknown dy dt now, but I need x and y. Well, here's the deal. I want to, what is my x value that I'm trying to calculate this at? 6, right? So I know this is 2 times 6 times dx dt, 1, plus 2 times, well, if x is 6, what is y when x is 6? 6 squared plus y squared equals 10 squared, right? I know when x is 6, I can calculate what y is. When x is 6, y is 8. And now I can solve that equation. I can calculate the actual change in position over time of the y value. Okay, so this is 12 plus 16 dy dt is equal to 0. Subtract over the, sorry, I can't write and talk. Subtract the negative, the 12 over to the other side, divide by 16, so dy dt is negative 12 sixteenths. 0.75. Yeah. And it's interesting that it's negative because in terms of position, it's going downward, right? So we say it's a negative 0.75 feet per second, or 0.75 feet per second in the negative direction. Questions about that? Okay, let's try something different. A water tank has the shape of an inverted circular cone with a base radius 2 meters and a height 4 meters. If the water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay. Let me read that again. A water tank has the shape of an inverted circular cone. The base radius, which in this case is like the top of the cone, the base radius, 2 meters, and its height, full height, is 4 meters. If the water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, so when we don't know what we're doing yet, let's just draw a picture. So we got an inverted circular cone, right? And we know the radius of that cone is 2 meters. And the full height is 4 meters. Let's establish what we know. We know that dV dt, the change in volume over time, is 2 meters cubed per minute. We want to find the rate at which the water level is rising. Well, okay, I know that's what I want to try to look for, right? I know that's my end goal, the rate at which the water level is rising. So what do I really want to calculate there? The rate at which the water level is rising. Well, the water level would be here. Then if I add more water here, then add more water here, then add more water here. What rate am I actually going to calculate? What's changing there as I change my water level, besides the volume? I know the volume is changing, but what's also changing in there? Think about water level. What's going to change as I increase in my water level? The height of that cone, right? Changing the rate at which the water level is rising, or calculating at the rate at which the water level is rising, is really calculating dH dt. That's what we're looking for. When do we want to calculate dH dt? When the water is 3 meters deep. Okay, so now let's somehow create an equation that links volume to height. Oh, the volume of a cone formula does that for me, right? The volume of a cone formula is equal to 1/3 pi r squared h. 1/3 pi r squared h. Let's find the derivative. Actually, not yet. Because if I go to try to take the derivative right now, isn't there another variable in there? I've got r in there, right? Okay, I would be taking something like dV dt is equal to 1/3 pi times 2r dr dt times dH dt. Do I know anything about dr dt? No. But I do know that when the height is 3, I want to calculate this rate of change of dH dt, right? Let's look at something. Maybe we know what the radius is going to be when the height is 3. Think about this piece in here, right? I'm just going to pull that out. This was 2, and this is 4, right? This full length in here was 4. I want to know when height is 3, what is my radius? Aren't those similar triangles? Aren't those two nested triangles? And they're similar by angle, right? So what I can say is 4/2 is equal to 3/r. For some reason I left h in. Hopefully that's not going to come back to bite me. This is another one of those things where I'm like, should I just do it the way I have in my page? No, let's run it this. Let's run it this way. So cross multiply, divide. 4r is equal to 6. So r is equal to 3/2. Let's say 1.5. You know what? I lied. Let's do 3/2. Why do I say that? Because I've got a fraction in here, and I think I'm going to need to use fractions. Okay, so in other words, volume is equal to 1/3 pi times 3/2 squared times h. This comes out right. I'm doing something different on my paper, and I really like. Oh, I think this is gonna be all right. I think it's gonna be all right. Volume is equal to, so that means this is 9/4, right? So 9/4 times 3, 12 pi h, which that's 3/4 pi h. Let's find the derivative. Okay, so that means now we have dv dt is equal to 3/4 pi. Is there anything acting on h? No. dh dt. Do I know dv dt? Yeah, I do. It's 2. Yeah, this is going to be fun. 2 is equal to 3/4 pi dh dt. So we solve for dh dt. We say 2 divided by 3/4 pi, which is 0.84. Yep, 0.8488. dh dt. Now let's label it accordingly. Meters per minute. 0.8488 meters per minute. Questions about that? Let's do one more, and then we'll save this searchlight problem. This is a good one. The searchlight problem. We'll save that one for the day we get back. The book introduces like this problem-solving strategy, which it's like, I mean, duh, you're going to do this anyway. But these problems you're finding are all going in the same route. Okay, step 1, read the problem carefully. Really? You're going to tell me to read? Step 2, draw a diagram. Duh. I mean, if you're going to try to draw a diagram as much as possible. Introduce the notation. Set it up. Set up what you know, set up what you don't know. Express the given information in the required rate in terms of derivatives, right? Write an equation that relates the various quantities of the problem. Honestly, that is the difficult part. Figuring out how the two quantities relate to one another and being able to put that in equation form so you can take the derivative. You're going to have to use the chain rule if there's something happening to it, and then you substitute in and solve. All right. Car A is traveling westward at 50 miles per hour. Car B is traveling northward at 60 miles per hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Let me read that again, because we're supposed to read the problem carefully. Car A is traveling west at 50 miles per hour. Car B is traveling north at 60 miles per hour. Both are headed for the intersection of those two roads. What rate are the cars approaching one another when the car A is 0.3 miles away and car B is 0.4 miles away from the intersection? Okay, let's draw our diagram. Okay, so we got these two roads, right? Car A is traveling westward. So here is car A. Here is car A. Yep. It's traveling westward Let's put this as an x, right? Because it's a horizontal. It's traveling westward at a rate of 50 miles per hour. Okay. You could call this negative 50 because it's going west, it's going left, but I'm just going to say 50 miles per hour. And you know what? I need to move this because that should not go there. I have another car B. Okay. They both look like box trucks. Car B, let's use our y value. Traveling north at a rate of 60 miles per hour. So dy dt is equal to 60 miles per hour. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles? Okay, so obviously car B is traveling at a higher rate than car A, right? How do I calculate the rate at which the cars are approaching each other? Well, think about this. I've got this other quantity out here, right? Let's call this z. Isn't z the distance between the two cars? So what am I really looking for? I want to see how fast z is changing, right? I want to know the rate of change of z. So really, I'm going to calculate dz dt. That's what I want to know. I want to know dz dt. Well, what type of equation relates x, y, and z to one another? Pythagorean theorem. So we can say that x squared plus y squared equals z squared. We take the derivative first, and we say 2x dx dt plus 2y dy dt is equal to, 2z, forgot my 2z, oh, that's purple. Okay, I don't want purple. 2z dz dt. Again, none of those can just be the straight up derivative because all of the, whenever, again, think about it, rate of change in terms of time, right? There's no time in here. So I'm not just going to straight up find the derivative. I've got to use implicit differentiation for all three of these variables. Okay, I know a lot of things in here. I know a lot of things. I know I've got, let's plug in, 2 times x. Well, what is x? 0.3 times dx dt times 50 plus 2y. Oh, sorry. Forgot dx dt. Plus 2y. Well, what is y? Yeah. 50's dx dt. We good? Say what?
Shouldn't it just be 50?
Oh, that's why. Sorry. Yeah, I plugged it in and then I said I forgot to write it. Oops. And then 2 times y, which is 0.4. See, you guys are understanding. You can just accept something that I write to be true. Times dy dt, which is 60. And then we don't write dy dt, right? Time is equal to 2z. Now, do we know what z is? Can we calculate z when x is 0.3 and y is 0.4? Yeah. 0.3 squared plus 0.4 squared is equal to what? Z squared. That's a 3, 4, 5, isn't it? So what is z? 0.5. Yeah, I could run the work, but yeah, 0.5. Now, times dz dt, right? Because dz dt is our unknown. All right, let's put the whole left side in. 2 times 0.3 times 50. plus 2 times 0.4 times 60. 78 is equal to 2 well, what is 2 times 0.5? 1. Get out. Is equal to dz dt. Okay. How fast are these cars approaching one another? At a rate of 78 miles per hour. That's how fast these cars are approaching one another. Pretty cool, right? Yeah. Oh, my. Those are kind of cool. Again, did we learn anything new? No. It's all just application. Okay, let me stop the video.